Hey, this is Brock Lemires. We're continuing our study of embedded systems design by looking at the SPI peripheral on the MSP430. In this video, we're going to walk through how to set up the SPI interface to send a byte as the SPI master. And we will go through a program example and view it with an oscilloscope and logic analyzer. So let's set up a task first, and then we'll walk through all the settings in order to configure it. So what I want to do is set up the SPI to be a master, and I want to have a clock, S clock, that's 100 kilohertz, and I would like to just send the data 4D out over the peripheral, and we're just going to drop it into the transmit buffer, and then we'll do a delay loop, and then drop it in again, then do a delay loop, and we'll sit there and spit out 4D over and over and over forever. And I'm going to use the A0 peripheral. So we've looked at the UART, and we were using the A1 peripheral because that was the application UART that we could send information up to the terminal. This time, let's use the A0 peripheral, which happens to just come out to pin other pins on the launchpad board. But this is the task ahead of us, okay? So we're going to, in order to get 100 kilohertz, we need to have SM clock as 1 megahertz because it's higher, we can't get it with 32 kilohertz. So we'll choose SM as a clock. We'll divide it by 10 to get 100 kilohertz, and then we'll set up the system with mainly the default values for everything. Okay, remember, when you set up the peripheral, you do similar steps as with the UART. First thing is you put the system into software reset by setting the UC software reset bit in the control register. Then you initialize all the serial configuration registers, and then you configure the ports, and then you clear the software reset, and then you can enable interrupts if you are going to use them, okay? All right, so let's take a look at the control word register, okay? So this will be the A0 control word register. There's a whole bunch of stuff in here, but the first and foremost, when you come down to turn this thing into SPI mode, okay, you use the UC sync bit, and that's synchronous versus unsynchronous. Unsynchronous is the default, and that's the UART. And then when you flip this into SPI mode, which is synchronous by setting the UC sync bit to 1, the bit fields in here actually change. And so this table, I've drawn it, and I've redrawn it from what it was in UART mode, and I've highlighted in gray the ones that actually change. And so it's kind of important to make sure that you don't look at the control word register for SPI mode because it doesn't make any sense. You have to actually go into the data sheet and look into it's the Monster Users Guide, and look at the control word register bit fields for SPI mode. But I drew it for you, so you can just look at this. So that's how we put this into SPI mode. Then we look at the clock. So also within this register, this is where we get to select which clock source we're going to use. The default is a pin on the MCU, but we also can choose the internal clocks, A clock, 32 kilohertz, which actually comes from a crystal, and then the SM clock, which is 1 megahertz. Okay, so we can choose those. The divider for that, or the scaler, is in the same register that we use with the UART, so the UC baud rate register, but now it's called bit rate. Okay, and it's the only setting that you have to divide the clock down. There's no modulation, it's simply a divider. So you put the integer value you want into this register, and that will give you what you need. So for our example, we're going to choose SM clock, give us a 1 megahertz, and then we'll divide it by 10, and that'll give us 100 kilohertz, okay? There's a couple of clock settings you can also do, such as the phase and the polarity. The phase has to do with, the default is, the clock is low, and then it goes high. That's when it generates the first bit, and then the receiver receives it on the falling edge of the clock, so that the latching edge is right in the middle of the bit period. Well, you can reverse that so that the clock is generated on the falling edge, and then the receiver can latch it on the rising edge. Then you can also change the clock polarity so that it's either when it's idle, it's low, or it's idle when it's high. And so you basically just invert the clock right there. Then we can choose, we go and we set up the SPI mode. So once we're in SPI mode, then there's settings for the SPI. So first and foremost, the UC MST, which is master bit, that configures whether you are in a slave or master mode. The default is slave. You can also then configure the STE configuration, which is the slave transmit enable. And this is if you're the master, right? Actually, it's whether you're in slave or master. But You can be in 3-pin mode, which means that you don't generate a slave transmit enable, or you can be in 4-pin mode, which is where you use a slave transmit enable, and then you can have 2 different settings here that are either high or low. Then you have this I2C mode. That's only used for the B0 and B1 peripheral. So if we're using A0 and A1, we don't have to worry about that, but they just have that in the documentation. Well, actually, I drew that because we'll use it later. Okay, and then you also have what the mode is for when you're in master mode. So how you actually use STE, okay? And so you can read through this. One time it's used to prevent conflicts with other masters, and that's in a situation where you actually have multiple masters, okay? So there's configurations for that, how that's handled automatically. Then when we go to the data framing, there's actually 2 settings for the data framing. So you can choose to have LSB first, which is the default, or you can do MSB first, and that's in the UCMSB bit. And you can also change the data length from 8 to 7. 8 is the default. In most cases, we want to use the default values. So consider clock phase, clock polarity, and frames. Those are the way that they are, okay? Those are what we want for the default, the most common SPI configuration. And then even the mode, right? It's 3-pin SPI. That's what we're going to use right now. We're not going to generate an STE right now, so we don't have to do anything for that. And if we're not using STE, then we don't have to worry about the UC stem bit. So we don't have a ton of settings, kind of like in the UART where we use a lot of the default settings. Once you have that set up, remember, you have to tell the MCU to not use the default functions for the pins, which is the ports. You want to tell it to use the SPI pins. So on the A0 peripheral, which we're using, the SPI pins are mapped into port 1, bits 4, 5, 6, and 7. S clock is on port bit 5, slave out, master in is on bit 6, and then slave in, master out is on bit 7. Okay, and in this example, we don't use STE, but it does come out to a pin. We'll set up all 3 of them, even though we're not going to use the master in. Okay, once we get everything set up, the theory is that we just drop information into the transmit buffer and it goes automatically. And that's what we're going to do it here. We'll just use delay to space it out. And then what's cool about it is the A0 S clock and SIMO, which is where we'll see the data, they just come out to pins on this J1 header, and we can actually drop an oscilloscope. We can put oscilloscope probes on this and just watch it. Okay, all right, so let's fire it up. Let's do this example. So go ahead and fire up CCS. And let's do a new CCS project. And we are going to be called, we're still in C, but now we're going to do SPI, and we'll do transmit 1 example. And we'll just do hex on A0. Okay, on A0. Okay, pretty simple. We're in C. Life is good. Okay, all right, so here's our little skeleton here. Let's go ahead and nuke that comment header. And then we're off. Okay, so first thing we want to do is set up SPI A0. Okay, we want to first put it into software reset. So UC A0 now this is key. UC is just universal serial. A0 now tells it that we're going into the configuration registers for A0. So now this is CTLW0, that's a control word 0 register, and I want to bitwise or with a mask called UCSWRST, and that is put A0 into software reset. Okay, now we're safe and we can start doing configurations. Let's do the clock all at once. So we still go into UC A0 CTLW0. Okay, so we're going to go in here and let's choose SM clock. So I'm going to do a bit set on UC SSEL __ SM clock, and that is choose SM clock, and now let's divide it by 10. And so, but to divide by 10, I drop integer 10 into the bit rate register. So UC A0 BRW, and I just simply put 10 in there. So then I do set prescaler to 10. Okay, and that'll to get S clock equals, and that's 1 megahertz divided by 10 equals 100 kilohertz. So that's going to give us the clock rate we want. Okay, so now we got the clocks all going. Let's set up, let's put it into, let's do the SPI modes. Okay, so those are also in UCA0 CTLW0. And let's put it into SPI mode by setting the UC sync bit. So put A0 into SPI mode. And then we got to tell it we're going to do a master here. So I'm going to go this is also in the UC A0 CTW control word 0. And I'm going to set the UC MST bit. And that is put into SPI master. Okay, so we're in SPI mode and we're the master, and that's important because that means that the clock's going to be generated, or we're going to send the clock. So this clock frequency that we set up, that's going to head out to the outside world. Okay, so that's that. Actually, that's all we're going to do because we're going to accept the default frame settings, which is 8-bit LSB first, and we're going to accept the default clock polarity and behavior, and it'll look just like we drew out in prior videos. And so now let's configure the ports, okay? And we're configuring the ports. We need to use the function select registers, port 1 function select. So port 1 select 1 is equal to something. I'm going to type this out a little differently so I can remember what I'm doing. Port 1 select 0 is equal to something, okay? So what I want to do here is I'm trying to do the following. I want to do, let's set up port 1 bit 5 first, and I want this to use S clock, okay? And to do that, we need to set these as 0, 1. And now to remember where that came from, if I go back here, if I look at these settings that I need, all of them, all the function select registers for all the bits, 4, 5, 6, and 7, I always need settings of 0, 1 on these registers. So I can actually say, I can actually do this. Yeah, I can actually do, I'm going to copy and paste this, and then I'm going to go here, and then I'll copy and paste it, and for the reason of, why is it tabbing so much? For the reason of setting up 3 bits, okay? I want to set up clock, slave out, master in, and slave in, master out. So then I got to remember what I'm doing here. So port 5 is S clock. Okay, port 5 is S clock. Then let's set up bits. Let's do slave in, master out. So this is the one we're going to actually use. So this is bit 7. So this is slave in, master out, right? So slave in, master out. That's where we're going to be able to see our data come out. And then bit 6 would be slave out, master in. Now we're not going to use that. Okay, we're not using that, but it's cool to set it up. Okay, so anyway, now we're going to clear bit 5. Okay, and then here we're going to set bit 5. Okay, and then down here we're going to clear bit 7. And then right here, we're going to set bit 7. And then right here, we're going to clear bit 6. And then right here, we're going to set bit 6. Okay, so that sets all 3 of those functions up. And like I say, we're not going to use the master in, but that should be it. So port 1 select register, boom, 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 bit 5, bit 7, bit 6, and those correspond to S clock, SIMO, and SOMI. And now that's, we just to complete the port setup or the pin setup, we got to take it out of low power mode. So go to the port power module 5, control 0, and I need to clear the lock LPM 5-bit. So this is going to be turn on IO. Okay. All right. So that's cool. So now the only other thing to do is to take it out of software reset. I'm going to go into, here's the putting it into software reset right here. And so what I'll do is I'll take it out of software reset by now clearing it. So now I'm going to clear that bit, and that's going to take out of. Okay. And now let's think about what's next. It's all ready to go. So let's just go into a main loop, and we'll just dump a piece of data into the transmit buffer, and we will then delay a little bit. So I know I'm going to do a delay with a for loop, so go ahead and set that up, set up my loop variable, and here I go. So I'm going to go while 1, which means loop forever, and what do? I'm going to go UCA0 TX buff. Notice it's the same transmit buffer as when we did a UART. And I'm just going to say 0x4D, and that's it. So send x4D out over SPI, and that's it. It'll send it. And now I want to delay a little bit, so let's go for I is equal to 0, and then we'll go as long as I is less than 10,000, and then we'll say I equals, let's do, yeah, I equals I plus 1, and that is actually it. So now it should just continually pump out 4D, and we should be able to see that on those pins. So let's go ahead and fire this up. We'll fix our typos first. Okay, what typos do we have here? Let's see, you probably saw it. Lockout, oh man, that one. Okay, so I'm gonna come up here. Oh, got a semicolon there, and then my lock LPM, misspell that, that's pretty common, apparently. So low power mode, it helps if you say it out, low power mode. Okay, is there any others? Okay, that might do it. No, one more, no big deal. Bit, what's bit? Line 18, bit 5. Okay, nice. All right, let's clean that up. Okay. All right, so there it is. So now let's take a look at the board. So I have my board plugged in here, and notice that I'm not going to be able to see if anything's happening because it's not like it goes to the LEDs. So the only way I can look at this SPI bus is with the oscilloscope. So I'm going to use the analog discovery oscilloscope, and I'm going to go ahead and grab channel 1 of the oscilloscope and hook it to S clock, which is on port bit 5. And if you don't remember that, it's right here. Okay, so port 1 bit 5. And then we'll go over to channel 2 now, and we'll go to port 1 bit 7, and that's all I need to care about right now. So then let's go ahead and let's take their negative channels and go ahead and hook it to ground. And always good to ground, things. Ground that. Luckily this Launchpad boards has grounds everywhere. So ground, and then we'll do just the scope ground together. So ground. Okay, so now we got that, and so now I'm going to fire up my analog discovery waveform tool and bring open the scope. And so here's my oscilloscope, and now I'm sitting here, and I'll just leave both on for now, and I'll just hit run, and then it's ready to go, and it's running, and it's not seeing anything. Now I'm going to come over here, and I'll put this way down here, and we'll hit run. Okay, ready, and go. Oh, there's something. Okay, so I see something. Let's move channel 1 and channel 2 down so I can see. Let's see here. So grab channel 2, put that down there. Here they are. So now my trigger is set on, it's still setting on, it's on rising, whatever. And let's see, I'm going to zoom in. Oh my goodness, look at this. So this is cool. So let me, let's see. So I want to separate these channels a little bit. So channel 1, instead of being 500 millivolts, let's do 1 volt. So that shrinks that down a little bit, and then let's do 1 volt on this guy, and let's see what I got here. So channel 1 is S clock. Okay, so look at S clock right there. That is awesome. Okay, let me zoom out a little. One, boom. Okay, so look at this thing, and oh, look at this. Okay, so this is it. This is awesome. So here's S clock. So it goes 1, 2, 3, 4, 5, 6, 7, 8. And that corresponds to the following piece of data. So remember, it's basically, it generates the bit on the rising edge, and then it's supposed to be latched on the falling. So when I look at this, the receiver will determine whether it's a 1 or a 0 based on the falling. So this is basically 1, 0, 1, 1, 0, 0, 1, 0. And so it's like, okay, that's awesome. And this is repeating over and over and over. And if I kind of zoom way out, it's doing the little thing where it's like, here's a blip, here's 4D, then there's 4D. Awesome. Okay, so now here's the question though. We got to remember whether that's the right information. So here's a screenshot I did of that measurement, and I noticed I got 1 0 1 1 0 0 1 0. Well, remember that's LSB first. So if I flip that over, the bit pattern I get is actually 0 1 0 0 1101. Well, that happens to be 4D. So I get it. I'm getting exactly what I expect. The other thing I'm kind of interested in is what's the clock frequency. So let me drag a little measurement on here, and lo and behold, it's 105-ish, 105 kilohertz. Not exactly 100 kilohertz, is it? But that's all right, because so what? It's close enough. It's the best that the MSP430 could do. And that's just due to the variation in the crystal. So we did it. We sent our first SPI out. Now, once we get into like looking at data, another really cool tool is a logic analyzer. And a logic analyzer basically says, instead of giving you the analog voltage like an oscilloscope does, it's just going to say, I'm just going to give you a 1 or a 0. So it basically just has a threshold level, and it says if you're below this, you're a 0. If you're above this, it's a 1. And the reason that that's cool is because sometimes you only care about the logic values, but since the measurement is simpler, it can have more channels. So the analog discovery, for example, has 16 logic analyzer channels on it. So let's do that. So I'm going to come back to my board, and I'm going to disconnect the oscilloscope, and I'm going to go over and I'm going to grab 2 channels of a logic analyzer, which they're labeled 0 and 1. And I'm going to put 0 on port 1 bit 5, and I'll put channel 1 on 7, which will be our data. Okay, so I got that, and then I got the ground on there. And I'm going to come back into analog discovery, and I want to go back home. So let's go to the welcome screen, and I'm going to set up logic. Okay, and then I'm ready to go ahead and set this up. So let's add some signals first, and we'll see this. Okay, so click to add channels. Let's just add a signal, and I'm going to add 0 and 1. Okay, and then let's just see what happens if I run. Okay, so I'm going to run, and I do get my little blip on there. So this is pretty cool. I am seeing a little blip on there. So now what I want to do is let's set up the trigger on here. So let's do a pulse trigger. So what I want to do, remember, trigger is where it finds a pattern and then puts it at t equals 0 on the screen. So if I go to pulse, what I can do is I can say DIO 0, which is the clock. I can say, why don't you trigger when you get a pulse less than, let's say, 5 microseconds. And that corresponds to the period of a 100 kilohertz clock. But so we could do like 6 microseconds. And so if I do that, it sees it, and then it locks it in. So it's like, oh, okay. So now let me zoom in now that I see what's happening here. And look at this. Lo and behold, again, we are able to see the information. So here's S clock, 1, 2, 3, 4, 5, 6, 7, 8. And then there's the data. And notice that the data now, it's not an analog waveform, it's a digital waveform. And this is really cool because one of the things that you can do with a logic analyzer is it actually has the bus features, which will allow it to interpret the data, and it'll decode it for you. Now in this situation, all the decoding consists of just flipping LSB and MSB, but it can actually tell us the hex value of it. So to do that, come over here and go add, right click over here and go add SPI. And we're going to have a SPI bus here, and it's going to ask you for what all the signals are. So for example, clock is going to be on DIO 0, data is on DIO 1, 8 bits, and then it's going to be LSB first, and then this is active low, rising, we leave the default of that, and for select we can actually do none, so we'll do none on that, and that should do it. We want to see it in hex. So let's go ahead and add that on there. It's going to take the information that I just created or just gave, and look at what happens now. So now here is my clock and data, and here is the information. So I get to actually see 4D as a logic analyzer packet. It's like, holy cow, now this is getting powerful. And if you notice, well, you can't zoom out too far, I guess. And so let's go back to position 0 is where the trigger is. So now I zoom out. And anyway, look at that. That is awesome. So now this is really cool. This is powerful because now this allows us to actually see the packet in its decoded form. And now we can actually see if our logic is right using the logic analyzer. All right, that's awesome. We did a whole lot right there. So nice work. That's our first SPI transmit. We looked at it with a oscilloscope, and we learned about a logic analyzer. So nice work. As always, support my channel by subscribing, and see ya.